everyone. I'm sorry for the delay in getting started. I am now using Keynote iCloud to present this, so hopefully, if there's like a few slides with broken animations, then hopefully we can work our way through it. Let's see if the clicker clicks. There it is. Okay, so I'm Andrew. I'm a game developer. I've been in the industry since 2004. At the moment I work for a company called Spry Fox. We just launched Alphabet 2 last week. You should go and download it. And for the purposes of this meeting, the important thing is this title here, which is the F1 series of games that I worked on for 2010 and 2011, which form the basis of this talk. Okay, so we're going to talk a little bit today about how AI works in racing games. I know you're kind of like a mixed group, so I'll try and explain the concepts as I go, but if there's something that I brush over that you're like, no one in this room understood that, please put your hand up and stop me, okay? So we're going to talk about steering behaviours, which is a common technique in the industry for doing steering for different entities and different applications. We're going to talk about why it doesn't work so well in some situations. A new approach that we used on F1 2011 called context steering that fixes many of the problems that were affecting our specific application. And then further things we can do with context steering in the future. So steering behaviours themselves promise a lot. Click, click. Okay, there we go. So they were initially put forward by Craig Reynolds in the early 90s. There's a very famous web demo called Boyds that maybe you've seen in the past, where you can go to his webpage and you can see this huge flock running around, and he's really, really good. I mean, part of the reason it's so successful as a technique, I think, is possibly because his website was so good at explaining it and how it worked. But the promise is that it's a nice, lightweight framework for building these kind of emergent steering systems. The behaviours are nice and simple. They're all self-contained. They're all mostly stateless, and you can drop one in and take one out, and everything just keeps working. And hopefully, when you put all these things together, you end up with emergent behaviour. The Boyds demo had a big flock that was moving around the screen as one big unit, and even though there was no code in there saying, please everyone keep together as a unit, it just all emerged out of the individual small stateless behaviours that they had. But they're not perfect. And when you try to use them in certain situations, they break, like any algorithm, right? There are certain degenerate cases where they don't work. And we based, F1 2010 was our first F1 game, and we based it off the code for Codemasters rally games. And the rally games used steering behaviours. So F1 2010 used steering behaviours, heavily modified steering behaviours, to make the F1 cars race around the track. And it was a huge, huge pain in the arse to get them working well. And I'll explain why. But one of the reasons, to illustrate why that was a problem, I'll talk you through like a degenerate, like a pathologically bad case of steering behaviours, and hopefully you can see what I'm trying to get at. So let's pretend it's not a racing car, it's an entity that moves on a 2D field, so it can move up and down, left and right. And we're going to give it steering behaviours, and we're going to give it a couple of simple behaviours that will let it move in an interesting way, and it will look good to a player. So the first one will add a chase behaviour. So let's say we've got some objects in the scene that we want to chase, other entities, enemies, or whatever they are. Pizza, like this guy who likes pizza. And so our chase behaviours can be really simple. We're going to just find the nearest object, and then the way steering behaviours work is your behaviour will return a vector towards the object. And the vector, the direction, is important. The direction is the way the entity wants to go, but also the length is how badly it wants to go that way. And so we're going to return a vector towards the object we want to chase, and we're going to make the length proportional to how close we are. So when we're far away from objects, we'll move relatively slowly, and when we get close, we'll start to move faster. And that works great. If we leave it running like that, that's fine. It returns a vector. Excuse me. The steering code will then take that vector and then just turn that into a velocity and start moving in that direction. But let's make it more interesting. Let's add an avoid behaviour. So now we'll add an obstacle that we don't want to hit, and the way we'll make this behaviour work is we'll return a vector away from objects we don't want to hit with a length proportional to how close we are to the object. So you can see we've got a vector going towards the left now. So left to its own devices, this would move the object to the left away. Left to its own devices, the chase behavior would move it to the right, towards. And then the steer code will take those things, and it just simply averages them all out. And then you can imagine what happens. The animations work. I'm so excited. You get zero movement, and so the behavior, the player will see your entity just sit stock still. And the player will say, well, there's another, I can see why it doesn't want to go to the right, but there's another guy to the left. So why doesn't it go chase that pizza? And it'll be very confused why your system is not behaving intuitively. So there are fixes like these are well-known problems. There are various approaches people try, and we'll go through them, and you can see why. Like they kind of work. They kind of work just enough that you can ship a AAA racing game and still win a BAFTA, but it would have been a pain. So first of all, we can ignore the chase. So we can say if we recognise that we've reached, let's call it like equilibrium, we've reached this balanced point where all our vectors are zero, then we can just do something like turn off the low priority behaviours. So we can say chase isn't as high priority as avoid, so we'll just turn that off. And then that will turn off the green behaviour, and the object will start moving to the entity will start moving to the left. That's good. And it even looks kind of clever because it's now moving towards the other pizza. And so we're like, well, like it looks intelligent, but if we move that pizza, then all of a sudden it doesn't look intelligent again. It's moving away from a wall when it could be moving up towards an object. So that's not quite good enough. We can chase both targets. So the object could the chase behavior could return a vector both towards the near could return a vector towards all entities. So it could return something pointing to the right that's quite strong because it's close to that entity, and then the other entity is quite far away, so return a smaller arrow to the left. And when you end up summing all of those arrows, you end up with a very slight, click, no, we've gone too far, it'll end up with a very slight arrow to the left, so it'll start moving to the left. But it doesn't move very fast. The avoid behaviour wanted to move really fast away from this obstacle, and we've ended up with a steering output that's moving us slowly away from the obstacle, because the sum of all those three vectors was very slightly to the left. So that's not good either. And so the last one, the one most people end up doing, and the one we ended up doing on F1 2010, was to validate, can you guess, validate the target before the chase. So in a situation you could ravecast or path find to the entity that you want to chase, and in this situation you would see, oh, I can't reach it, so I'll just ignore it, and I'll choose the other one instead. So we get no right-hand vector, we get a small left vector as a chase, and a large left vector as an avoid. And when you sum those, that's great, it moves away. And it moves fast away as well. And if we do our cheaty thing from before, remove the second entity, then it still all works. Like you sum those things, oh, now I'm going to click all those animations. It sums all those things together, and you get an end result that points up and to the left, so it's going to move away and kind of loop upwards. The design flaw here is that we are returning not enough information from our behaviours. Our behaviours are returning where they'd like to go, their answer, rather than how they reach that decision. So, when you put that all together, the problem with steering behaviours in our situation was there was no guaranteed movement constraint. You saw that. We were able to return a bunch of vectors that made the avoid behaviour react more slowly than it wanted to, which is bad. Especially if you can imagine if that obstacle was coming really quickly towards you, and the avoid vector wanted to move very quickly out of the way, it wouldn't be able to in some situations. It leads to inconsistent decisions, so you could flip-flop, like you could, sitting in this stasis position when you should be moving, or you can imagine a flip-flopping scenario. And the end result is that it works, despite all these drawbacks, it works great for this application. If you're dealing with a large amount of entities, and all those entities are observed from outside, so we're going to look at this big flock and we're going to look at move around emergently, it works great. It's simple, it's lightweight. But when you want to be inside the flock, when you want to be one of the birds, that's when it breaks down. Because we've had to to solve this problem, we've had to make chase aware of avoid. We've had to put all of the awareness of the world and the obstacles into the chase behavior. And if we want to add another behavior, I don't know, like another kind of behavior, like an attraction behavior, that's also going to need to know about the world, because it's going to have the same problem. And this is exactly the problem we had in 2010, because the behaviors were trying to act independently, and when that happened, they were all hitting each other. So we had to basically put collision avoidance code in every single behavior, and the end, like, to avoid like this kind of pile-up. And the end result is you might as well have a big if statement, because if every single behavior is going to know about object avoidance anyway, and then some of them ended up having to know about overtaking to make overtaking more smooth, it turns into this megalithic system, monolithic system that's hard to debug, that's very tangled, it's not stateless anymore. It's basically breaking all of the promises that we had for steering behaviors. So why even use it? Why not just go to, like, we just use one big if statement? So for 2011, we went back to the drawing board, and the core design goal that I wanted for the new system was that we were going to have separate behaviors because that's nice, it's debuggable, it's easy to work with, it's easy to balance, but we're going to make sure that these behaviors are returning why they're making a decision rather than the decision that they made. And then we'll let something else take all the contexts of all those decisions. The fact that the chase behavior would say, there's a guy really close to me and a guy far away from me. You do with that information what you will. And the obstacle avoidance code would say, there's a wall really close and I think you should move away. Do with that information what you will. And then something else would resolve that wall. And hopefully, we'll end up with less code that's easy to maintain and would look better. Like it will perform better for the player. So the system we came up with is called the context behavior system because it merges these context lines. And it was kind of structured like this. So we have a context controller object, and that contained a bunch of context behaviors. And these are the same thing as our steering behaviors. That the promise is that they're small and lightweight and stateless, easy to test, easy to tweak, easy to debug. And then we're going to take an object that I'm going to call a context map, and that's going to contain all of the information about the world that these behaviors find interesting. Well, they're going to fill it up with that information. And inside it, what it's really going to be, we're going to break it down into two things. We're going to break it down into interest and danger. And interest is going to be the things that I would really like to be closer to, the things that I find more interesting. And danger is obviously going to be the things I really want to stay away from. So we're going to take those two maps and we'll pass them to all the behaviors. And then the behaviors will populate them as they pass through. And then afterwards, we'll process those maps. And we'll try to come up with a resulting steer that satisfies everyone. And so what is a map? I struggled with it for ages. Like I knew I needed something that was a map. I knew what the metaphor was, but I didn't know what the actual data representation was. And in the end, it was relatively simple. It's just an array of floats. So we take, this is my programmer art version of an array of floats. And what we're going to do is correlate every direction that we could possibly want to go in to one of these slots. So let's say we're going to move in the 8 cardinal directions, then we're going to take each of those directions and map them to one slot in the map. And the idea being that we can then look, say it's the interest map, we can look at a high value in this slot and correlate it. I'm not going to say that word anymore. What's a synonym? Can you say synonym?
Correlate?
Yes, yeah, that word. A line, I like it, with the southern direction. It's really, okay, we're interested in the southern direction. And so you can imagine it's kind of like a rasterization of the entity's view, as if it was a camera, as if this was, and in fact, this metaphor will come back again and again, a one-dimensional picture, a one-dimensional bitmap of the world from the viewpoint of the entity. So let's go through, let's re-implement our entity problem, our 2D entity problem, but in this new system. So we've got our two maps, danger and interest. We've got our 8 cardinal directions. And then we're going to add in a chase behavior. So just like before, we've got 2 entities. And we're going to take the first entity, we'll iterate through them, And because it's relatively close, we're going to put quite a lot of interest in the corresponding slot in the map. And then we'll iterate through all the possible directions. And we'll say this direction, this brings us somewhat closer to the entity we want to chase, but not super close. So we'll put in a low value there. And we'll do the same on the other side. And then we can do the same, we can evaluate the other object and do exactly the same thing, except because it's further away, these values are going to be smaller. So that's it, that's our chase behaviour done. That was stateless, that was quick, and it had no need to have knowledge of obstacles at all. So then we bring an obstacle in, we bring our avoid behaviour in, and we do the same thing. So we know there's a lot of danger in this direction. And so we write in a high value for that slot in the danger map. And then the other two directions bring us closer than we would like to be in that way. So we write a little bit of danger to those areas. And we end up with these kind of, like, these make for lovely debug graphs. Like, there was a mode in F1 where you could race around and it would be like a frequency graph, like constantly going boing, boing, boing as you drive around in front of your car. It's really cool. And you know if your code is starting to produce really good debug, then it's probably good code. So then we're going to process those maps, and this is the point where you can't really generalize this step. This is kind of going to be unique to every application of context steering. So for 2D entity steering, this is what you could do. We're going to take all those danger areas, we definitely don't want to go that way, and we're going to mask them out and then apply that mask to the interest map. And then we're simply going to pick the remaining slot with the highest value interest, and then we're going to move that way. Which should look like this. Does it move? It moves. Come on, move. There you go. And so what we've got is something that is simple and stateless and resulted in an interesting, sensible behaviour to the player, and then it moved towards the other object because it couldn't move to the right. And it knew it couldn't move to the right. But at no point did the chase behaviour have to know about anything about obstacle avoidance. So let's apply that to F1 and see what that looked like on a real shipping game. And the thing about racing games have a lot of metadata, the tracks are fixed, you're always going forwards. It's not like a street game where you can turn left at any point. You're always going forwards. You know where the next corner is. There's a lot of markup, and the one thing we will always have is a racing line. We know where the left side of the track is, we know where the right side of the track is, we know where the racing line is, and often, if you turn off, at least in 2010, and probably all racing games are similar, we could turn off this steering code completely, and the car will still go around the track. It knows how to brake for corners, and it knows how to accelerate out corners, and it knows how to steer around corners. So we don't have to worry about that so much as part of our steering system. What our steering system needs to do is do interesting overtakes, avoid other cars, draft, other interesting things like that. And so the output of the system is very slight movements left or right, and then sometimes it might be a brake. But other than that, we don't need to tell it to accelerate, we don't need to tell it to do anything like that. But, so it's a relatively segregated system from how you move on a track. So the way we're going to projection map this is take a bunch of slots relative to the racing line, left and right, and then map those to our context map. And you can see the green one at the moment correlates with where the racing line is. But later on, as we get towards the apex of the corner, the racing line might be over here somewhere. And so the race line, this isn't centered around the racing line, it's centered between the two edges of the track. And then how are we going to write up behaviours? So let's do some relatively simple behaviours. The first one is a racing line. So if we're off the racing line for some reason, this will move us back towards the racing line without having to do anything about it. And that's simply look at each slot and how far away is it from the racing line. And the ones that are near the racing line are going to get more interest. And I'll put it in the interest map. Then let's do some avoiding. There's a car to our right. I hope you all like my ProgramR F1 cars, by the way. It's slightly overlapping us, so we're going to put some values into the danger map for that. And it's going to correlate to where that car is, the blue arrow, and there's a little bit of danger for the left and the right, because we don't want to get too close, even though it's not quite intersecting, we don't want to get too close. Let's do another one, draft. So drafting in racing games is, or in real-life racing as well, is if you can get behind another car that's moving fast, it can break up the air for you, and then you can use more, you can more efficiently drive at high speed, and then sometimes it would allow you to do an overtake. So drafting would be a cool behaviour for us to do. And let's do that by evaluating each car in turn that's in front of us, and then we're going to write some interest into the map depending on how far that car is, because further away, well, the less effective the draft is. And so this one's relatively near, so it's going to get a lot of interest here. And this one's relatively close to the racing line, so it gets a little bit of interest there. I haven't discussed, by the way, how we merge these maps. So if you have, it's simply just the maximum value. So if we want to write a value in here for interest, and it doesn't happen to be greater than what's already there, then we just discard it. So it's just remembering the maximum value it's seen at any one point. So how do we then process these things? We've got these two maps. We know where the racing car is, and you can see now how this is why I say that these are different for every application, because since we're not moving on a 2D plane, even though there's a lot of interest here, to get there we have to go through quite a lot of danger, because we have to move across the track. And so we'll process this map by doing something similar to what we did before, except we're going to flood filter left and right, and at the moment the danger starts to increase, which is here, we're just going to mask out that and everything else. So we're masking out this slot even though there's no danger, because we can't reach it without increasing danger. And then we'll take that mask, apply it to the interest map, and then find the highest value interest that's left. And what that looks like in practice is that we will avoid this dangerous draft that includes going through a cover, and we'll move slightly to the left, slightly off the racing line, to draft this car here. And to the player that looks like a good, emergent, sensible behaviour, and we've done it with nice, simple, stateless behaviours. No one bleeding any context anywhere. So, some of you may be wondering, like if I only have 8 cardinal directions, my entity moving on a 2D plane is going to look very robotic as it moves around. And so one way to fix that is, of course, just to have a tremendous amount of slots in your grid, but that gets expensive. But you can actually, because this is, as we said, like a one-dimensional bitmap, we can take some graphical concepts and apply them to it. So we can use techniques that the graphics programmers would use to do things like enlarge an image, and we can do subpixel rendering. So let's say we want to take, like the steering code has said, this is the slot to take. So what we're going to do is take the gradients of the slot around it, and then try and find where the maximal value is. And that ends up there. And we can, even with 4 directions, we can produce a vector that's non-cardinal and end up going southeast. And so you can end up with quite detailed, granular behaviours, despite having quite a coarse map. Performance. So it is relatively expensive compared to steering behaviours. Steering behaviours, you know, it's like 2 or 3. In the ideal world, it's 2 or 3 vector calculations and you return vectors. So they're relatively simple. Whereas here we're doing quite a lot of rasterization and it gets relatively expensive. Luckily, you can do things to limit the cost, like we'll talk in a second about level of detail, but we can use, again, something from graphics world, we can use vectorization and SIMD to operate on this one-dimensional array in a really quick, parallel, non-pipeline busting way, so we can get fast again. And then level of detail, we can take, it's really resilient to having, like we just discussed, really resilient to having coarse maps. So the player might have a really high quality map, and then a car that's far behind it can get away with having a really, really coarse map. And it's still going to obey those constraints on collision avoidance, because if you render a lot of danger into the middle there, it's going to represent a wider array of danger rather than a narrow array of danger. It's going to represent a really over-the-top array of danger, and it's going to try and keep itself out of that danger. So it's still going to be able to keep out of it, it's just going to look more cautious than it needs to do. So that's one thing, and then you can do other fancy things, like if a car's really far ahead of you, then you can, but you'll see, if you can see it, even though it's a similar distance to the car behind, we can still give it a high level of detail by giving it a really finely grained map. and then this car that's right behind us, we're not necessarily looking at it, so we'll give it a course map as well, even though it's very close. And that way you can kind of throttle the CPU usage across the frame. The end result of all of this, by the way, was something like 11,000 lines less of code in the code base for a significantly better AI. And you could read the reviews of 2011 and they're talking about how the AI is like more interesting, does more overtakes, less cautious, and all of that came out of that system. So we do more stuff. We can take this 2D image, 1D image, and we can smooth it. So if you have a little spike of danger, then everything else around it looks pretty safe, then maybe you could ignore that. So if you apply some Gaussian smoothing or something, then you can dampen that down a little bit, and then maybe it won't affect so much. You can blend it with, you can save the previous frame's context map, and then average it with a new one. And so changes happen, rather than having something blipping in and out, you could have, for instance, if someone's braking sharply in front of you, and then unbraking, they might blip into the map for 1 second and disappear. You can have that gradually appear and then gradually fade out again. And that will, and that's something that steering behaviours can do as well. It's called hysteresis, where you remember what you did the previous frame and try and avoid flip-flopping between multiple decisions. But you had to write that into every single behaviour. You had to write each behaviour to have hysteresis. Whereas with context maps, you get it for free. You just blend it with the previous frame's map, and then all your behaviours are getting hysteresis for free. So to recap, we took a projection from decision space, from whatever, like racing lines or a 2D world or whatever, and we mapped that to a one-dimensional array. Our behaviours write world views into the danger and interest maps, like it's rendering a canvas view. And then we evaluate those maps for a best decision somehow, and we end up with a sensible, nice, interesting behaviour. Nice, decoupled stateless behaviours. We split up how an object is steering from why it's doing that steering, which is always good. We've still got emergent behaviour, or we've got a guaranteed movement constraint, which we didn't have before, and we're getting nice, consistent decisions. And it works at the macro scale, so it works when you're in an F1 car in a flock, it'll still keep working, which we didn't have before with steering behaviours. So that's it. I think if you want to learn more about this, you can go on my blog, and I wrote a chapter about it in BrumAI Pro 2, which is relatively old now, and so they put the PDFs for the chapters online, and if you go to my blog, you can find the PDF. You can also see this almost exact talk on the GDC vault. If you Google for the next vector, that'll be, I'm in half of that talk. Yeah, thank you very much.